And tell us about eigenvalues of rotations.
Thank you to the organizers for inviting me here. This has been really nice. So this is a paper we've done joint with Daniel Harder, who isn't here, and Corey, who is. So, oh, right. Okay. Surely I'm the person who needs this least, I think. But anyway, okay, so I guess I want to get into what the setting is first. So the spherical adjective, I don't know if it's been really defined yet, but it's kind of a nice place. So it's kind of an easy thing to understand. So, but I'll start with I guess the definition of this has been given in a lot of different ways. But the way I like to think about it really is it's sort of the prototype is the category of complex representations for a finite group. So when I say tensor categories, I guess the adjectives I like are, so unfortunately this word is a little bit ill-defined, but I like this to mean abelian, so like modules for some algebra. I like it to be C-linear, so that means the Hom spaces are complex vector spaces, and then monoidal, which is where we have our tensor structure and all the nice things that come with that, like the unit object and the associativity. Okay, so I might talk a little bit more about this piece in a bit, more than other people have, but I think this is a nice prototype. But then the other sort of points of view that I've come from are so representations of a finite, or I mean of a semi-simple Hop algebra. So the invariants I'll talk about in this talk actually were sort of inspired from these 2 points of view. And then finally, the last one is sort of the application we're going to take from here and move into the universe of the standard invariant for a finite depth, finite index subfactor, right? So this is sort of like the data of your planar algebra. So I'll also say something about those too. Okay, so this is just sort of a little map for the main examples. Okay, so so I'll give a more, so C is a tensor, so we have a tensor category, right, that has all those things. So the 2 additional things for it to be fusion are, 1, that it's finitely semi-simple, so we've already said what that is. And then 2 is rigid. So I just wanted to say this so I can point out the diagrams I like to use. So this is where we have an object. Every object you can associate a dual object, and then there are some nice morphisms. I like to read my diagrams going down. So we have our evaluation morphism, and then we have our dual basis morphism. So, and then these satisfy the so-called zigzag relations, which is to say that composing them in either of these ways gets you back to identity morphism. So this would be identity on X dual, and this is identity on X. Okay, so I just like this so I can define something later without having to appeal to too much extra notation. So we kind of have 2 main invariants for characterizing fusion categories. So I guess I didn't really spend much time on the motivation part, but I thought a lot of people have given that so far. But again, my main motivation really is also like Noah's. It's just like looking, like given some family, can we sort of figure out what all the associated tensor equivalence classes are? So the way I like to think about it is the following 2 invariants are sort of the main ones. We have the Grothendieck ring, right? So this is K0 of C. And this is just the Z-based ring with basis given by the irreducible element, or the simple objects isoclasses. And it's, I think, simply understood as just having, it's just the ring structure of the tensor category for getting these natural isomorphisms. Okay, So this together with the 6J symbols, which is essentially just the induced linear maps from the associativities. So these are the maps from this A right here. This is the natural isomorphism that goes for any triple of simples, x, y, z, and here C. This goes from x tensor y tensor z to x tensor y tensor z. Okay, so you can look at the induced linear maps on the Hom spaces. And these two things together completely characterize a tensor equivalence class for a fusion category. So if you know all this information, then you know there's only one tensor equivalence class that has this information. Okay, so so sort of the classification program I'm interested in is given a base ring, in other words, a fusion ring. So I'll just say a fusion ring, or Grothendieck ring, this K, something that looks like this K naught. What or how many tensor equivalence classes are associated to it? So in other words, what are the 6J symbols that go with this fusion ring? Okay, so there's actually been quite a bit of work done on this, and but it's in general a very difficult problem to do, because as you can see here, you end up with lots of sort of nonlinear equations. The equations come from this Pentagon axiom that's been, I don't think it's been written on the board yet, but it's essentially a commutative diagram that this thing has to satisfy. Okay, so you can do it that way, and in fact, so some examples. One, Tambari Yamagami, okay, they did it for fusion categories that have this this fusion ring, where G is an abelian group, and rho, so obviously your element multiplication is given by this group law, and then the multiplication for this guy is given in the following way, and then rho also just absorbs the G on either side. Okay, so these guys did it pretty much directly. They wrote down this fusion ring, and they came up with a bunch of equations and solved. And it's really like pages of brute force calculations. It's very hard, and it's also hard to generalize to other scenarios. But then along as the next are Azumi and then Evans and Gannon, sort of using Azumi's methods, we're able to sort of do this in an operator algebraic way, right, by realizing these categories as endomorphisms on Kuntz algebras, and then you can look at how these endomorphisms act on the generators, and essentially it gives you the same information as the 6J symbols, but it sort of bypasses the need to look at these equations. So this is the Kuntz algebra method, and one class they did was the near groups, which are simply the ones that look like this, but where you have an additional multiplicity of rho happening in the rho squared, and then also the Hagerup-Azumi categories for some ranks too. Okay, but maybe what we want is something a little bit better than this sort of program when we are looking at a fusion ring and want to figure out what categories go with it. Maybe we want to figure out some invariants that let us sort of bypass having to think about this. Okay, so I guess the zen of this this idea is that we want more for less. So we want more for less, and so the next the invariant that I really like is only for spherical categories, unfortunately. So we do have to specialize a little bit. Okay, so let me say that, and then I'll define my invariant. So, or not mine, but the invariant that we're interested in. So these are pivotal. So that's just to say that there's a natural isomorphism from this double dual to the identity functor on C. Okay, and then furthermore, we want the left and right traces to agree. So when we have some endomorphism of an object x in C, what we can do is, using this pivotal structure, we can define the quantum trace or pivotal trace on the left and the right. Okay, so we have f here, and then we can just, the idea is that we want to bring this all the way around, right? This is dual basis and evaluation, but we need this here to connect because we end up with a x star star here and an x here. Okay, and then the idea is that in the spherical case, if we do it on either side, it's the same. Okay, so this is if this is a number, right? Because it's this diagram is giving you a morphism from 1 to 1. So which is this is in here, which we know is isomorphic to C. Okay, so and then I didn't get to write this in, but this is the right one. Okay, but we want them to be equal, and you see the name comes from thinking about these diagrams not on a plane, but some sort of sphere, right, where you can take this string and sort of wrap it around in the back. Okay, so when we have this, and in fact, you really only need pivotal to define this, but we get better properties when we think spherical, because then we can appeal to the Drinfeld center, which I'll explain in a minute. But when we do this, we can define the Frobenius-Schur indicators. Okay, so they're named for Frobenius and Schur, and they were first defined for complex group representations in 1906. They were generalized to Hopf algebras by Susan Montgomery and her student Vitaly Lenchenko in 2000, and then later to the pivotal categories and quasi-Hopf algebras case by Richard Ng and Peter Schonberg. So that's the definition I'm going to give now. So I'll give it in terms of this rotation operator. Rotation and FS indicators. Okay, so we define the rotation operator in, so let's let X be in C. So from now on, C is spherical. So we define our rotation operator in the following way. It's a morphism from HOM, or a linear map from HOM 1 to X tensor n, or X tensored n times, to HOM C X tensored n times. Okay, and it's just this guy right here. So we take one of these morphisms, and then we come over here and just wrap this leg around here. Okay, so this is n times, obviously, and that is 2. Okay, so this is what I call, or we call, rotation for a spherical category. Just sort of a simple one-click rotation. Okay. 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 So, and then the indicator is simply defined in the following way. So we call these the higher Frobenius-Schur indicators, simply because classically the Frobenius-Schur indicator is just the second one where there's 2 objects here. Okay, so this is just the trace of this operator. And it's just the usual linear trace, too. Okay, and then let's see. So it's a theorem of Ng and Schonberg in 06, I think, that this is a categorical invariant. So that means to say that if F is an equivalence of categories, a tensor equivalence, okay, then nu n of x in C is equal to nu n of f of x in D. Okay, for all x in C and natural numbers. Okay, so there's a few nice properties of this guy. The one that we're going to use the most here, though, is that this is always a cyclotomic integer. Okay. Okay, so properties. So 1 nu n of x is cyclotomic integer. And another important property is that this sequence is periodic, and the period is known as the fs exponent. Okay, so that's a generalization of the exponent of a group. Okay, so this is nice. So let me just make a little, sidetrack. I guess another fact, and this is a theorem also of Ing and Chomp. So this is, I guess it probably should have its own number, but oh well. This is a theorem of Ing and Schomburg as well. I think this was from the year after '07. So so the fact is that these indicators can be obtained from the modular data, that is the S and T matrices of the Drinfeld center, which has been defined a few times already, so I won't do that. But this is just a category with whose objects are pairs, where the objects come from C, but except this time they're paired with half braidings. Okay, so it's a theorem of Muger that this is modular, and you can use the modular data to find the indicators in C. Okay. If it's spherical. So this is where we need the spherical condition. Okay. Okay, and then it's also, this is sort of equivalent to, I don't know if it's a theorem or an observation of, I'll just credit it to Izumi though, that we can find them from the tube algebra, which basically carries the same information as this. Okay. So let's see. Oh, I'm sorry. I actually don't. This is not what I wanted to say. This is actually, it's actually better than this. From the T matrix alone, and I'm sorry, that was not a good theorem. So it's actually just from the T matrix and the functor that's the adjoint, so the functor I that's the adjoint to forgetful. So if we have Z of C forget to C, we have something called the induction matrix, also from Muger, that goes in the other direction. Okay, so forget what I said before. The S matrix, we don't want that. Because again, we want more from less. So usually these twists are somewhat easier to obtain. Okay, sorry about that. Okay. Okay, I think I've gotten this out of order a little bit. Okay, yeah, so like I said here, this functor here and the T matrix. So the idea is that now we want to obtain the eigenvalues for rotations, but maybe we want it to be a little bit more general than the one I showed you to start with, where it crosses over the vacuum. Okay, so I think I've gotten this out of order a little bit, sorry. Okay, pardon me for 1 minute. Okay, yeah, so this is a little out of order. Okay, so let's, So let's go forward a little bit to the so-called generalized rotations and the generalized Frobenius-Schur indicators. Okay, so these were defined more recently by Ing and Johnberg and used to some advantage, especially in this proof of the rank finiteness conjecture for modular categories and some other things. Okay, so let me give you the generalized rotation. So let's I'll call f just the forgetful functor from z of c to c. And then we want to let A be an object in z of c. Okay, so I've tried to stick with A, B's, and C's for objects in center and X, Y's, and Z's for objects in C. So hopefully that pattern continues. Okay, so let's get our generalized rotation out here. So this one is going to be more in the vein of what people expect from the study of planar algebras. So we want to go, this is going to be an operator on the Hom spaces in C from this object forgotten with the half braid structure forgotten, okay, to the n-fold tensor product of of X. Yeah. Okay, and it goes like this. So this time we do have a little stick up here coming from f of A. But this time, even though we have forgotten, we still want to use the one morphism that we kind of pull out from the center that gives us this braiding. Okay, and so, oops, not there, here. So now we could just bring this around as before. But we were able to pass into this because we used this half braiding that was associated up here, okay, in this place here. And then again, the generalized FS indicator, okay, is this guy right here. Now the problem is, these guys here, you do need the S matrix to obtain them. So this theorem isn't true for these. You need the full S and T matrix and this information too to obtain them from the center. Okay, so in some sense, you really want to just have this stuff because we want to stick with this less is more idea. Okay. Okay, so that's where our first theorem comes from. Yes. So let's say irreducible for now. I mean, there might be usually what you do to deal with that is there's some additional sum somewhere. So, but in this theorem it'll be an irreducible. So I'm going to erase that. Sorry, I got my notes out of order a bit. Okay, so here's our first theorem. Okay, so we have an object in C, and then let's say an irreducible object in Z of C. Okay, so number one, so this shouldn't be too surprising, but the eigenvalues of this generalized rotation are nth roots of this twist, theta A inverse. So I didn't say what this is, but this is just going to be the entry of the T matrix for A. So again, this is why we want to stick with irreducible here, because this will give something a bit nicer. Okay, and then an eigenvalue. Okay, maybe I should. I'm writing too big. Okay, well, it's all right. I'll go over here. Okay. Okay, so then we have a little formula, which is nice. Okay, so an eigenvalue omega has multiplicity given by the following formula. Multiplicity, this capital P comma x super A of omega. So this is a number, and the formula for P is given by x, the sum from k equals 0 to n minus 1 of, so I'm going to write something here that I haven't defined yet. Okay, this is, I guess this is, I've already called something generalized FS indicator, so maybe you could call this the generalized FS indicator. But the point of this guy is that this k here just is saying that instead of taking the trace of this one generalized rotation that wraps around back here, we're doing it k times. Okay, so it's the trace of this guy performed k times. Okay, but that's still not good because like I said, we really want to kind of get back to the case where we're only interested in these guys here. Okay, so let me give the formula for that, or this is where the changeover. So, oh, and in general, so there is a general formula too. So I'm going to erase this. I think it's okay. Before I write the sort of translation into the just usual FS indicator. We have a general formula if B is just any object in here. Okay, then we call the multiplicity K now. I think this is in line with notation from planar algebras. Okay, so this is just a sum along here. So maybe this isn't even worth writing, but just to get it out here. So again, this is your entry here, and then this is the dimension Hom V of C B A. I'm writing way too big. Multiplied by this. Okay, so it's just some kind of weighted sum of these things. Okay, so really this is the important theorem, or the important formula. Okay, so so now let's try to reduce to the one rotation case. All right. Okay. Okay, I'm looking up here. Okay, so okay, so the idea here is that we can sort of make this translation in the following way. What we can do is just divide and take the indicators over the D-fold tensor product, where D is the GCD. Okay, if it's not 1. Okay, so pictorially, this is like saying, okay, we're going to, what we want to do instead is, instead of doing this D times, maybe we're going to take a whole bunch of, a whole D-fold tensor product and wrap it at once. Okay, that's the graphic idea of thinking about this. And then we get the following equality. So this allows us to prove the following theorem. Okay, so now we have this. Okay, so we're back to a, so again, this is, I guess, the generalized one, but we're back to a single rotation, or a single rotation over this fold tensor product. Okay, so, and then where this alpha kn, this is the Frobenius element. So this is where the proof of this really relies on the fact that we're in this cyclotomic field, because this is the Frobenius element of the Galois group of the nth cyclotomic extension. Okay, so when the GCD is 1. Okay, so the point is just to apply this over and over again until we have that being the case. Okay, so we have this. So now what about some applications? So oh wait, no, well, I guess it doesn't matter. Okay, so let's talk about some rigidity phenomena. Okay, so this is the case where we want to think about what I was talking about before. When can we take some fusion ring and look at some sort of a priori weaker invariant that actually turns out to establish everything, or to distinguish every tensor equivalence class associated to the fusion ring. So, so one, let's just talk about the, we'll just call it indicator rigidity. Okay, so this is a property of a given fusion ring. So the idea is that if we have two categorifications, that have the same fusion ring K, okay, then if nu K, so this actually gives us a correspondence here. Because of this, we don't get equivalence, but we do get a correspondence on the objects. That correspond to basis elements here. So maybe on just the simple objects, but then you get one on the objects. Okay, so if we have this, so when I write the same x, that is to say these correspond based on this guy right here. Okay, if we have this, then when is it true that then these must be tensor equivalent? Okay, and I mean this for all x, or all simples. Okay, because we're semi-simple. Okay, so we actually do have some families that give us this. Okay, so theorem Sock-Johnson. I think 14, maybe. We know this is true for the Tambari-Yamagami categories. Okay. Another theorem from me, 15. Okay. So we know this is true for near groups with the multiplicity of rho. So okay, I'll just write multiplicity of rho in the square, in rho square is equal to the order of the group minus 1, and it's true for this guy is equal to the order of the group when this is odd and less than or equal to order 13. So this was just from the computations of Evans and Gannon. Okay, so and it's conjectured that it's actually a conjecture of Evans and Gannon that that the modular data for the centers of these guys is given by some sort of what I'll call a generalized Weil representation, which is basically being given by some quadratic forms on this group and another associated group. So if that's true, then we would get this being true for many more categories. So remember the near groups, this is the guys that do this, and this is the guys that have a multiplicity here. So again, these both fall in Izumi's framework of quadratic categories. Okay, but unfortunately, in doing our calculations, we figured out, this is something I didn't really think about when I was doing the near groups before, that we actually have a counterexample for this. VJT. Okay, so this is not true for the Hagerup fusion rule. So that is to say, in the parlance of Penhas's talk, is this guy right here. Okay, so there's actually there's two unitary fusion categories with the same higher Frobenius-Schur data, but they are inequivalent as tensor categories. Okay, but interestingly enough, there's two non-unitary ones that correspond to this too, also from Evans and Gannon's 2015 paper, and at least the indicators still do distinguish between whether it's unitary or not. So I guess that's one nice thing. Okay. So, but we might have we do have a weaker rigidity. No, in this case, you just need the ones that come from one. Yeah. Yeah, I misspoke about that a little bit earlier. Okay. Okay, so I guess my hopes were dashed on this a little bit, but anyway, it's nice to know that it's not true for this family of fusion rings.
Maybe you should mention it was conjectured that it was always true.
Yeah, it was. There was a conjecture, I guess, by Richard Ng that this should be true for quadratic categories in general, but as you can see, it's not the case. And you can actually obtain this from direct construction or direct calculation by using the information from David and Terry's paper. Okay, so okay, how about another rigidity phenomena? So this is called annular indicator rigidity. Okay, so let me give you my definition of planar algebra that I think I'm most comfortable with is this, or at least now, thanks to Corey. This is a commutative algebra object in the representation category of an annular temporally Leib-Jones category. Okay, so this is actually tensor equivalent if you're more comfortable with the center of this incompletion of TLJ op. Okay, so this is like the temporally Leib-Jones category, but instead our string diagrams are happening on like an annulus instead of just a plane. Okay, so what happens here, and I think this is I think this must be a theorem of Jones, but if we have an object in C, then you can construct a planar algebra A with weight in vector This weight in vector space is given in the following way. Okay. And as is the case with subfactors, if A tensor A star generates C, then you can recover C from this information. Okay. Okay, so now what we want to do is so now let's suppose that C and D, again, are categorifications of a based ring or a fusion ring. Just something that looks like a Grothendieck ring. Oh, I'm sorry, these are spherical. Okay. So again, so we want to be able to use our indicators. Okay, so again, this gives you this nice identification of objects. Because they both drop down to K by the K naught functor. And then we have this nice annular rigidity theorem. Just because we can get the rotation eigenvalues now. Okay, so theorem. Okay, so annular indicator rigidity. Okay, so the idea is that now our theorem says that K naught C and the higher FS data of C. So our previous theorem shows that this determines these guys so in particular, in this situation where these are both categorifications of K, if so I write HFS for this. If this data is the same in the appropriate way, in other words, under this identification given by the squiggly arrow, okay, and the following two objects are identified by the squiggly arrow, then the planar algebra that we can build from these guys must be isomorphic in this rep annular TLJ category. Okay, so this is good. All right, so not too bad. We don't have this other guy over here, the indicator rigidity, but we still have this. Okay, so very useful for sort of going ahead with classification problems. Okay, so what did I do with the? Oh, there it is. Okay, so I guess it looks like I probably don't have time to get to the second word in the title, which is braids, but it's essentially an application of this. But just let me say that so since fusion categories for subfactors are generated by an object like this guy, then this recovers the category. When we pick the one that generates, right? you can see that the failure of indicator rigidity sort of relies on the fact that that the commutative algebra structure on this thing, on this object, isn't unique in rep TL and annular TLJ. So maybe for future work, the question is, what could characterize base rings that have a unique, whose categorifications have an object like this with a unique commutative algebra structure? And then that would give us new families that have the indicator rigidity property, or new fusion rings with the indicator rigidity property. So it kind of gives us a new route to maybe finding some other families that actually do have this property, because clearly we do know some that do, based on their fusion rings. Okay, and then I guess I didn't get to the details of this, but I will say, since I still have 5 minutes, I just want to describe the application of this. So the second application is for these braid eigenvalues. Okay, so now let's C be modular or premodular. We have results in either case, but in the modular case in particular, it boils down into getting these braid eigenvalues from S and T matrices, which is nice. So if you just want to think modular, it's okay. So for an object A and C, there are braid group reps that come about in the obvious way just from looking at the diagrammatic calculus. So we're looking at representations of the braid group on N generators into this space of endomorphisms of n-fold tensor products of A. Okay, so using our eigenvalue multiplicity counting theorem, we can actually compute the eigenvalues of pi n A of sigma for a nice class of sigma. So just to end, I'll draw a picture of this sigma, these sigma guys. And it actually is nice that this class contains actually contains the generators of the braid group and the periodic braids, which I believe is defined as those if you raise them to a certain or of enough power, then they end up in the center of the braid group. Okay, so it's these guys here. So this is why I probably only have a little time left, because drawing this is hard for me. Okay, so cross over this way and then go back around back. Okay, so this is L, this is our N here, and this is M. So for any guys that look like this, then we can determine the eigenvalues under these representations. Okay, and it's just another formula in terms of that K formula that I've erased now. But then when it's modular, it reduces to coming from the S and T matrix. And there's some nice pictures that show how the proof goes about, but I think I'm out of time, and I've said really what I want to say. So thank you very much. Yeah.
A really basic question, but the thetas, the ribbon elements.
Right. It's these guys.
So how hard is it to read off, just say from A and what the data of like the underlying object and the half braiding? How hard is it to read off what the eigenvalue is? Is it something really easy?
Say that again?
Like if you don't know what if you haven't computed the whole Drinfeld center,
Right.
you just have an object and a half braiding.
Right.
Easy to read off what theta is.
Oh, I think, but I'm actually not sure. I'm not sure about the answer to that. I know that if you want to find this generalized indicator with A, you just need to know the half braiding for A. Right. But as far as theta, that's a good question. I kind of don't think, because it's just this, right? So you just need to know the half braiding. Yeah, in the pivotal structure. But that comes from the category itself. So I guess so, yeah, because this is with the.
Oh, you just have braiding with itself.
Yeah.
Somehow you're meant to be in a situation where what you know about the Drinfeld center is maybe it's T matrix, and you don't know what the half ratings look like, and that's where you use things like this to try to get more from just the modular data where you don't actually know the half ratings.
Right.
Because there's lots of ways now with Scott's modular data machine to compute this without knowing anything else about the category. So what else can you get from the modular data without having to know what the half ratings are?
That's kind of the wrong question.
Yeah.
So is there an obstruction to going back the other way here in this theorem?
Oh no, I don't think so. I think because these.
Or is it just the same?
I think that this because basically what you're doing is when you drop you're throwing away taking traces of these guys here. Oh, you're saying if you just have the eigenvalues of the rotations. No, I think that it's this is something you could easily get back.
You don't know how to put an algebra. This is just as an object in Rep ATL. This isomorphism is not as algebra, so you don't know how to put an algebra structure on it if you just have an object in.
Right, but I mean, I'm not asking for the algebra back. I just want the higher Frobenius shirt data. Let's see.
Oh yeah, you can get that back.
So this is-
Yeah.
Take the trace.
These are one-to-one corresponding.
Yep.
Yeah, because and this would just be the easier direction.
Okay, any more questions?